Hello, welcome to the Agru Advantage Technical Series webinar. Today's topic is the final cover system advantage that's offered by Agru products and final cover geosynthetic systems. A little bit about your host, myself. I received a bachelor's in civil engineering from San Jose State University here in California back in 1987. I've been a registered civil engineer in California since 1991. I've been specializing in environmental engineering with solid waste management and containment systems, along with hydrology and hydraulics. I've worked in the construction industry for Piazza Construction, was a South Bay builder back in the early 80s. Spent time with engineering consultants, engineering associates, Harding Lawson Associates, Brown Caldwell, Golder Associates. Also a stint in the public sector with the Sacramento County Department of Waste Management and Recycling. And I now consult to Agru America. Active member of SWANA, ASCE, ASTM, and have publications in various trade shows and magazines as listed there. Today we're going to have an introductory presentation on geosynthetic capping systems. This is part one of likely a four-part series on this topic. This first introductory phase is going to present some of the history of the geosynthetic industry and materials and how we got to where we are today, and just some of the issues involved with capping systems. Now there's different capping system versions. First of all, there's geomembrane and soil composites. Pretty common, everyone's seen them. They're in use all over the United States and Canada and across the world. They, however, require soil depth suitable to the selected vegetative community required to hold the whole system, topsoil system, together. Stability is based on veneer interface strengths. And then there's the synthetic turf cover, or in Agru's case, the closure turf final cover system, wherein the synthetic turf replaces a soil erosion protection layer. It protects the underlying geomembrane from UV radiation, and stability is a lesser concern than with the geomembrane soil composite, other than landfill gas pressure forming beneath it in landfills. Then there's exposed geomembrane covers. These are by far the cheapest alternative using geosynthetics. They are, however, subject to ultraviolet degradation, so they're really nothing more than a temporary cover. Stability is a lesser concern other than wind uplift, hence some exposed membranes you'll see anchored down with sandbags on ropes, or there's percussion anchors, are called platypuses, can be driven into the subgrade soil to help hold the whole system down. Then there's the monosoil or water balance or evapotranspirative cover, depending on what theory you prescribe to. These are technically feasible for drier climates, in general those with a annual average precipitation of less than or equal to 19 inches per year. These systems require an appropriate fine-grained soil and long-rooted vegetative community, and their stability is based on soil internal shear strength and erosion resistance. Well, today we're going to focus on two of these in analyzing system stability. First off is the geomembrane soil composite, and then the synthetic turf cover. And that to answer the question, why is this important? Why is stability design so important? Well, two words, Kettleman Hills. Kettleman Hills was a Class 1 or hazardous waste facility in the south central valley of California, or the San Joaquin Valley, Desert-like region, very dry, very low rainfall, and it was a perfect location for hazardous waste materials. Now the module in question was this one. This was module B17, and back in March of 1988, on the morning at 6:30 in the morning on March 19th, a half-inch crack was first observed on a truck ramp into the module. By noon, the waste mass had displaced by several feet. It was a huge litigious issue. MCON Associates was the design engineer at the time. I had joined MCON Associates in the summer of 1988, just a few months after this occurrence. I had never seen so many lawyers running around a company before in my life, and neither have I since. At issue with the B19 slope failure was the fact it was a very complex composite liner system. Secondary liners, primary liners, assorted Vado zone monitoring systems, and just all sorts of interfaces. Now, one thing about all these liners, these HDPE liners, they were all smooth. Now, interface sliding along these interfaces happened in two locations. Along the base liner in the lower slope, it occurred between the HDPE geomembrane and the compacted clay liner. Along the slope, it occurred between the geonet and the liner, another HDPE liner, and generally took many years and much court time later to resolve this whole situation. Or here's another two words for you. The Cheerin Landfill in Pennsylvania had a slope failure in this location, and that is a headline that I would not want to have my name associated with. So slope failures, they're a risk in any system, but if only they don't, in short. Now, what was the result of the Kettleman Hills failure in particular was improvements to testing materials used in these systems. In particular, adoption of the 12-inch direct shear test, or modern method ASTM D5321, was first adopted in 1992, about 4 years after Kettleman Hills. Here's a picture of the TRI friction testing laboratory in Austin, Texas. They pretty much got this down to an assembly line. And then increasing use of textured materials. Here's a photo of Agru's MicroSpike liner. The purpose of the texture is to increase interface shear strength to avoid the slippage that occurred at Kettleman. Now, there's a couple of schools of thought on running a direct shear test. Now, first, for the fixed interfaces, you'll see here that the first geomembrane is fixed on this side, and then the upper geomembrane is clamped on the other side, and then a shear force is applied with corresponding normal load to drag this geomembrane across this geomembrane. One thing about this test style is it does isolate the interface of interest, or this one. The flip side of that is this really a material shear strength test, or is it a material tensile strength test? Right? What's to prevent, with this side clamped, what's to prevent a tensile force from developing in either this geomembrane or this one down here? For the free interfaces, Same test box setup, normal load, applied shear load, and then here's in a floating condition here's several geosynthetics, a geotextile, a geomembrane, geosynthetic clay layer, and a geocomposite. This test method will determine the weakest failure plane in between all of these interfaces that you see here, the gravel to the geotextile, any of these geosynthetics to each other, or the geocomposite to the subgrade soil beneath. It cannot isolate a specific interface of interest. Now, as far as precision and bias, one thing you have to know about the direct shear test is results are not absolute. For precision, there's none established. ASTM D5321 says the precision of this test method is being established. It's said that since 1992. Bias, there are no direct data to determine bias. And what I mean by bias are differences in results between different labs or different lab technicians who all have their different approaches to setting up the test box, or whether they properly compacted the soil or what have you. Now that I've got you sufficiently bummed out about this test method, there is accuracy in the method. Here's two charts of geosynthetic to soil. Or actually, this is textured HDPE to a non-woven needle punch geotextile. So a geotextile cushion, or say like a geocomposite. Now there's accuracy in the method because you'll see here these R coefficients, or coefficient of correlation, has a highest possible value of 1. Here we've got 0.96 for the peak test, 0.95 for the residual strength test or long deformation test. These are very accurate results. So in general, the results will show a trend that you can count on. And then within a certain precision. So the precision is simply this point to this point. What's the probability of your test results or your design falling within this range of results. There are two different direct shear test result types. There would be the brittle failure, which is typical of stiff clays, dense sands, dry of optimum compacted clays, textured geomembranes versus geotextiles, some reinforced GCLs, and then geosynthetics with all of the soils listed above, such that there's a failure in soil. Ductile failure is associated with soft clays, loose sands, wet of optimum compacted clays, smooth geomembranes versus other interfaces, and then reinforced GCL, so they can play both sides of that fence. And then, of course, geosynthetics with the soils listed above. Now, those normal strength curves that you'll see on a DST result will look like this. You'll have over here for brittle failure a discerned gap between the peak strength curve and the residual or long deformation curve down here below. And then for ductile failure, they're pretty much the same. Now, some interpretation of the test results. First question is, to peak or not to peak? So when you see those test results, you'll see a peak value and then dropping off to some residual value down here. Now, whether you use that peak value or not depends on the engineering parameters or engineering philosophy of your particular firm or organization. For example, some engineers ignore peak strength altogether in stability design. That's very true out here in the West, along in California, where we spell seismic with a capital S. Others will use the weakest peak strength interface to select the residual shear strength envelope for design. Both approaches have validity. It really depends on the particular philosophy of the organization you're with. Now, another interpretation is to moor or secant. Now, this Moore Coulomb envelope here is out of classic soil mechanics. Moore envelope is defined by a slope angle and then an intercept point down here called cohesion or adhesion, depending on whether it's a clay or coarse grained soil. Secant projects the strength results, strength versus normal stress results, through zero. So it assumes no cohesion or no adhesion. Again, it depends on the design parameters or the engineering philosophy of your organization. For interfaces with no natural adhesion, it really doesn't matter. However, secant strength can be determined from a single point. Now, there's two schools of thought on this as well. One thing secant will do through a single point is give you a much higher shear interface angle. As you can see here, this angle versus this one is steeper. What you do lose performing this type of strength calculation is that these lower normal loads, you're losing some design shear strength. So you're leaving some of that shear strength right here, you're leaving it on the table. One thing that all engineers will agree on is do not project either below nor above the DST data points. And the reason being is the Moore envelope, or the shear failure envelope, is actually more like a curve than a straight line. So these points here are defining a sector or segment, if you will, along this curve. It's not a true 100% accurate representation, but works well enough. Now, a little bit about adhesion or cohesion. Well, it does happen. Here's a sample of a geocomposite and a sample of Agru's MicroSpike. Lay the geocomposite on top of the MicroSpike at horizontal and then tip it. You can see that there is some natural adhesion between these two as the fibers of the geocomposite get stuck on the texturing. This is also known as the Velcro effect. Its design value is not clear. The Velcro effect is more prominent with blown film textures. It'll require the use of a rub sheet when installing over a geotextile material or installing a geotextile surface on the blown film sheet. That means more installation dollars, simply from the crew time that's required to move those materials around. Now, you might think that's good for shear strength, but you got to remember, unless the design has a normal load of 0, the Velcro effect may serve no useful design purpose. If the shear strength envelope of your system behaves like this, all the Velcro effect does is get in the way of installation, really. Now, towards construction of geosynthetics. First thing I'm going to show you here is with geomembranes, in particular polyethylene geomembranes, is the double wedge weld. Now, this is a thermal weld where this machine here produces a weld that looks something like this in profile. The lower sheet and upper sheet are fused together here and here, leaving an air pocket here in between them. And then a cut strip from that weld looks something like this. You can see that that diffusion weld on this side, and then over here on this side with the air channel in between them. Now what do you do with that air channel? Well, you pressure test it. And you see here air pressure testing done here and here on these double wedge welds in that direction and that direction. This is the data that's recorded during a air pressure test in that double wedge weld air channel. It's powered up to 30 psi and then held for 5 minutes. And if there's no loss in pressure, then it's a passing test. If there is loss in pressure, you're going to see a very unhappy liner installation foreman. The other welding technique is extrusion welding, or otherwise known as fillet welding. You'll find this done around penetrations for patches where destructive samples are taken to the double wedge welds, and then corners where panels. Now here's an example of a construction quality assurance test on a extrusion weld or a fillet weld. It's a vacuum box. It simply applies a soapy solution over the seam, as you see here, and then applies a vacuum and watches for soap bubbles bubbling up around the weld. And of course, this test method needs 4 to 5 supervisors all standing around watching it done. Now here's where you'll find extrusion weld locations. You'll find them around, say, this penetration here, a landfill gas vent of some sort, leachate collection system sump riser, Vado zone monitoring sump riser, other control panel installations, and I suppose a fire extinguisher would always be a good thing to have around a landfill. Some other basics for you are specifications for geosynthetic materials. A lot of these have been developed by the Geosynthetic Research Institute. You'll see here GRI GM13 for HDPE geomembranes, GM17 for linear low density polyethylene geomembranes, and then a host of others. Geotextile separators, GT13, GCL3 for geosynthetic clay liners, and then other procedures or test requirements for seams on the geomembranes. Here's a table out of one of those specifications. This is for high density polyethylene, has specifications for thickness, asperity height, or the height of the texturing, the density of the material, tensile properties, yield and break, tear resistance, puncture resistance, stress crack resistance, oxidative induction time. That's really a topic for another webinar, but basically how long this stuff will last in an exposed condition. And then carbon black content, which is all intended to accommodate the oxidative induction time. You'll probably see a lot of these more established firms. These are already written into their material specifications. This is pretty much a standard throughout the industry. Also, the GRI produces guides such as GC8 for geocomposite and GeoNet allowable flow rates. We'll get to that in the next webinar. Then other things like GCL design guides, sampling, GM sampling, geomembrane sampling techniques, and field test beds, lifetime prediction of geomembranes using time temperature superposition and Arrhenius modeling, another webinar topic. In addition, there's recommended practices, geotextile design strength, cold weather seaming, and a variety of others. All of these can be found at the Geosynthetics Institute website located at this location. Now, a little bit about the final cover veneer that we're going to leap into boldly next time as far as subsurface draining is, first let's start off with the rules or permitting. Now, all the final cover permit regulations and requirements have a basis in Federal Subtitle D. This is an overarching closure requirement for municipal solid waste landfills within the United States and its territories anyway. These regulations have also found their way into Canada, although Canada does not have an overarching federal authority like we do in the form of the EPA, and then also have been adopted elsewhere in the world. Now, first of all, Subtitle D requires all owners and operators of municipal solid waste landfill units to install a final cover system that is designed to minimize infiltration and erosion. The final cover system must be designed and constructed to have a permeability less than or equal to the permeability of any bottom liner system or natural subsoils present, or a permeability no greater than 1 times 10 to the minus 5 centimeters per second, whichever is less. And minimize infiltration through the closed landfill by use of an infiltration layer that contains a minimum 18 inches of earthen material at that permeability, and minimize erosion of that final cover by use of an erosion layer that contains a minimum 6 inches of earthen material that is capable of sustaining native plant growth. That's essentially it. Alternatives are allowed in a following clause. Some states have added requirements, such as Connecticut, California, New York. Viewers from Canada and elsewhere in the world may recognize some of these requirements in their own environmental regulations. In Canada, as adopted by the specific provinces. A little bit about the materials. Again, here's Agru's MicroSpike geomembrane. For really aggressive designs with a lot of shear strength requirements. There's also the Super Grip Net geomembrane. This is a combination, I call it a combination geomembrane and geonet. Studs on this side act as a drainage layer, and then these grips on the downside will dig into the subgrade soil and generally deliver much higher shear strengths. And then, of course, there's geocomposites for subsurface draining. Now, of those materials, MicroSpike comes in thicknesses from 30 mil to 100 mil. That's both in high-density polyethylene and linear low-density polyethylene, except 30 mil is not available in linear low-density materials. Super Grip Net or drain liner thickness is available from 50 to 100 mils in both resins, and both include the integrated drainage system, or IDS as we call it. The geocomposite thickness, those range from 200 to 300 mil, and those come either double or single-sided with 4 to 12 ounce non-woven geotextiles heat bonded to one or both sides, or neither side in the case of a geonet. And then the integrated drainage system, particular to the Super Grip Net or drain liner products, has a minimum thickness of 130 mil. Now, little bit about the typical veneer system. Now, the vegetative soil cover, or the erosion protection layer, is what we're going to start off with here. And that's over the drainage layer. That's either a geosynthetic or a granular drainage layer, geocomposite drainage layer depicted here. The barrier layer used to be clay soil and is now generally a geomembrane, a textured linear low geomembrane depicted here. Now the reason clay soils are not used so much anymore is that well, a lot of studies have been done showing that, well, A, they don't do well under differential settlement with landfills. Their elongation, strain elongation is generally about 2%, which means they crack easily. And then the vegetation growing down through them can desiccate them, leading them to shrink and crack. And in general, they just don't seal up well over the long run. And then finally the subgrade, or as we call it here in California, the foundation layer, upon which all of the above is built. Now, some of the key design elements for this system are cover soil permeability, or the ability of water to flow through this cover soil into the drainage layer, and then transmissivity of that drainage layer, or its ability to take that water percolating through and draining it away such that the cover soil does not become saturated. That's next webinar. And then there's interface friction strength between all of these components here. Those are the three really key design elements. There are others, but these are really key. Now, some of the forces acting on that final cover system are, well, first of all, rainfall, fire, well, not campfires, but wildfires, sliding of the cover soil or other components against each other, clogging of the drainage layer, be that a geocomposite or a granular drainage layer, and then landfill gas generation beneath the system, which will tend to lift it all up and away from the subgrade soil interface, erosion of the cover soil, settlement of the entire system, conditions such as here in the West and a few other parts of the country, the United States anyway. Now, some of the basic forces, well, there's sliding, in which case this final cover system, the soil on top of this final cover system just slid right off the geomembranes. And there's rainfall erosion, such as this mess, or what you'll more likely find on a system, a deep rill erosion down to the barrier geomembrane. Now, a lot of that is made even more critical in just how difficult it can be in getting a viable vegetative community thriving. Then there's landfill gas uplift. Technical term for this phenomenon is whale. This is a section of geomembrane that popped through an overlying soil cover and produces this nice pronounced gas bubble. There she blows. And then there's this phenomenon with landfill gas uplift. You'll see here a shredded remnants of a geomembrane and some other components conspicuously absent. Technical term for this phenomenon is just plain ouch. Then there's fire. Now this was a result of a wildfire that affected the environmental control systems for a landfill in Southern California. This led to things called the Reasonably Foreseeable Releases Regulation on non-water quality releases. This regulation requires a capital cost estimate to repair the damage from natural events such as earthquakes, maximum credible earthquake versus a maximum probable earthquake, or an earthquake that has a 10% chance of happening in a 50-year event or 50-year return period. Then there's flooding, the 1,000-year flood versus the 100-year flood. There's provisions for cost estimates for tsunamis. Applies to a handful of sites in California. Seiches. Well, that's a seiche is a back and forth wave on a lake. Whatever. Then there's precipitation, the 1,000-year 24-hour precipitation versus the 100-year 24-hour precipitation, and fire. Now, some in the state have accused this as an underground regulation. In certain circumstances, it's probably good to have money set aside for things like this. I mean, these are basically unpredictable events. They happen. They're not common, but when they do happen, they cause a lot of damage. And then the other force, another force that occurs on a final cover system is settlement. Now this can be an unseen, basically a disabling, destabilizing force on system subdrainage. And the reason being, now what that means is that water flowing down this slope here, whether there's a drainage layer present or not, it's not always there, is going to encounter this and start to pond and create a saturated layer of soil beneath the surface that won't be observed. Now this can create instability in the cover soil and weaknesses in this interface interactions here, and generally lead to an unstable condition. Now, how significant that is, there isn't any documented case load yet, but it is a risk. Now, for the next webinar sessions, again, this was just an introductory session. We're going to talk about climatology, what design rainfall precipitation should be used on final cover design. Should it be the HELP or the 5-minute intensity? Soil veneer, we'll talk a little bit about vegetation, the thickness of that soil veneer, the permeability of that soil, runoff coefficients, and then soil cover drainage layer. Maximum slope length L, that's allowable for the capacity of that drainage layer based on its transmissivity, also its interface shear strength. And then geomembrane as a barrier. Interface shear strength, static and seismic. Those will likely be 2 separate webinars. Landfill gas pressure relief systems, and also settlement. Those are all in the next 3 to 4 webinars, most likely 4 to come, or 3 to come following this one. So again, my name is Chris Richgels. I was your host today. If you have any questions, please give me a call at that phone number or email at that number. Also want to note that PDH credit is available for this webinar in certain states, not all of them. In particular, New York, Louisiana, and North Carolina, and Ohio. I believe we do not offer PDH credits in those states simply because of the credentialing requirements in those states. But most every other state in the country that requires continuing education for its registered civil engineers, give me a ring and we'll get you a 1-hour PDH credit for today. Other than that, if you have any questions, please give me a call, send me an email, and we'll chat some more. So anyway, thank you for attending. And again, give me a call, email, and we'll talk some more.